Hey everybody, welcome to today's video on isotopes and the technique that we use to study them, known as mass spectroscopy. All right, here's our periodic table. Notice that I've circled the element magnesium, so let's just zoom in and look at what the periodic table has to say about element number 12. So this 12 up above this symbol is, of course, the atomic number. Atomic number, simply the number of protons that atoms of magnesium have. Okay, that number has to be a whole number, it's a counting number, and it is unique to each element. So having 12 protons is what makes an atom magnesium. Okay, we also have this other number down here, which is not a counting number, and that's what I want to talk about today. That's known as atomic mass. Atomic mass is a weighted average of the masses of all the isotopes. Okay, so let's talk about this word isotopes. Do you remember back in first year chem, we would sometimes draw what we called a Bohr diagram for an element, and we would represent the nucleus where all of the protons live, where they hang out. And then, so for magnesium, 12 protons are in the nucleus, and then there are also 12 electrons outside the nucleus. We're going to talk a lot more about electrons in the days to come. So right now, really, I want to focus on the nucleus. And just a little side note here, have you ever wondered how it is that a bunch of like-charged particles, in this case 12 positive protons, could all be hanging out together in a really dense, compact area of the atom? It's due to something called the strong force. If you take physics, you'll probably talk about that a lot more, but it is very strong and it's capable of keeping like-charged particles together in very close contact with each other. Okay, that's really more something that physicists worry about, so I just wanted to throw that out there. Now, in chemistry, we do talk a lot about Coulombic attraction. So that's another force going on within the atom between the positive protons and the negative electrons. This Coulombic attraction for oppositely charged particles gives the atom its shape, keeps it together as a discrete unit. Okay, so back we go. We have 12 protons packed together in the nucleus and then electrons outside. But within the nucleus, we also have neutrons. And the neutrons are neutrally charged, and they serve kind of to give the atom some extra weight. So let me give you an analogy. Okay, that's my Bitmoji. Me all being all Zen-like, doing my yoga and being all calm. Okay, so that's my Bitmoji most of the time until we get close to Thanksgiving, which is my favorite holiday of the year because, you know, pie and stuffing. So when we come back to school after Thanksgiving, I might have to change my Bitmoji a little bit. Now, these are both me, and I've not changed in any way. I'm going to be the same person. It's just that one version of me is a little heavier than the other version of me. Same thing is true of atoms. So isotopes of an element have different numbers of neutrons and therefore different mass numbers. Within this nucleus of magnesium, where there are 12 protons, there might also be 12 neutrons. And that would give a mass number of 24. That particular isotope of magnesium is given this isotope notation. The mass number is written above the symbol, and the atomic number is written below. But that's not the only version or type of magnesium atoms that we find in the universe. There's also magnesium atoms that have 12 protons and 13 neutrons. So the mass number of those isotopes is 25, and they still act in every way like magnesium, but they're just a little bit heavier. And then there is yet a third version or a third isotope of magnesium called magnesium 26. It also has the 12 protons. It has to in order to be magnesium. But the mass number of this version, this isotope, is 26. So again, these are three different isotopes of magnesium. They differ from each other in their number of neutrons and therefore in their mass numbers. Now, on the periodic table, magnesium has the atomic number written above. Hey, by the way, this is just a little pet peeve of mine. On the periodic table, you're going to see the atomic number written above the symbol, but in an isotope notation, atomic number is written below. I don't know why. Sorry, I think that's kind of confusing. Okay, so on our periodic table, we have the atomic number, which is true for every single type of isotope of magnesium. But this number down here is not a whole number. It is not mass number of any of the isotopes. It is instead the weighted average of the masses of all the isotopes. So let's look more closely at how we come up with that weighted average. So we have the three different isotopes of magnesium. The first one here has mass 23.985. The second one is a little bit heavier. Again, it has that one additional neutron. And then the third isotope with 14 neutrons and 12 protons has the heaviest mass of all. Now, you might think it would be appropriate to add these three masses together and divide by 3. That is certainly how we calculate average. But what we're looking for here is not a simple average, but a weighted average. You know how in your classes your tests count for more than your homework assignments do? So the same thing is true when we're getting a weighted average for isotopes. We have to figure out which of these three isotopes is the most common, the most abundant. And it turns out that this magnesium 24 is by far the most abundant. Its abundance is 78.99%. Now, do you see how I wrote that percentage as a decimal? 78.99% expressed as a decimal is 0.7899. And then the abundance of magnesium 25 is 10%. See how I wrote that as a decimal? And the third isotope, the heaviest of all, is 11.01%. So what we're going to do is take each isotope's mass and multiply it by its abundance, expressed as a decimal, and we get this product. And then we're going to repeat for the second isotope, the mass of that isotope times its abundance, and we get this number. And then the third isotope, its mass times abundance, and we get this guy. I want to talk about abundance real quickly again. These three abundances, if they were written as percentages, they would add up to 100%. When we write them as decimals, they're going to add up to 1. You can verify that if you'd like. Okay, so our calculation was to take the mass of each isotope and multiply by its abundance to get a number. We do that all the way through, and then we're going to take these three numbers and simply add them together. And that gives us the weighted average. known as atomic mass. The weighted average of the masses of all of the isotopes, and that is the number that you would find on the periodic table. Okay, now the last thing is to talk about how do these abundance numbers get figured. And by the way, no matter where the magnesium comes from, no matter where the sample is found, the abundances of the 3 isotopes is fixed. Okay, the sample is always going to give you 78.99% for this isotope, etc. Okay, so the way we find those abundances is to use a technique called mass spectroscopy. And that technique uses a device called a mass spectrometer. So let's take a look at how this guy works. First of all, your sample of magnesium, which is a mixture of the 3 isotopes, is inserted into the device here. The first thing that's going to happen to those magnesium atoms is that they're going to be bombarded by ionizing radiation. The purpose of that is to convert these neutral atoms into ions by knocking off an electron. Okay, so that process which removes an electron from each atom is not going to alter the mass of each of those atoms. The mass of an electron is about 2,000 times smaller than a mass of a proton. So it's sort of like me hoping to lose a little weight by trimming my bangs. Okay, it's inconsequential. So once all of these magnesium atoms, the various isotopes, are ionized by dislodging an electron, now they're positive particles which can be affected by tweaking electric plates in the device and causing this beam of isotopes to be deflected. And the deal is that the lightweight isotopes will be deflected a lot. And the heavier isotopes get deflected only a little. And along the sides of this tube in the mass spectrometer, there are places which will detect the isotopes as they get deflected. So the machine is literally going, oh, boop, oh, there's a lightweight isotope. It hit me right there. Here comes another one. Here comes a third one. All these lightweight guys are hitting in this spot. And the heavier ones, which don't get bent very far, deflect right here. Oh, there's a heavy one. Oh, here comes some more lightweight ones. Oh, here's a medium weight one, which gets deflected somewhere in between. And so the ability for this device to detect the lightweight guys and the heavy guys and the ones in between, the net effect is for it to generate a graph, which is called a mass spectrum. The graph is the mass spectrum. The device is the mass spectrometer. Okay, so let's look at a blow up of the mass spectrum. Sure enough, the isotope called magnesium-24 has the greatest abundance, and the other 2 isotopes have a much lower abundance. And it is those abundances that we used in this calculation to come up with our weighted average or atomic mass. Okay, guys, I hope that was helpful.